So, we start with this particular session where we take it from where we left in the previous session. So, if you recall, we in the previous session discussed about the mathematical foundations of the conservation principles, in a way that how the physical principles can be translated to a general mathematical form, which is typically either one partial differential equation or a system of partial differential equations, each describing the conservation of one particular parameter, be it mass, momentum, energy, etc. Now, we need to develop the methodologies by which we are going to solve these equations, and to do that we have to understand first is, if we do not solve the equations in a particular way, but keep a broader frame in mind that we want to understand maybe the flow, pressure, temperature, etc., how we can do that, the different ways, and what are the pros and cons, and what is that specific thing that we will consider as the one of the ways to do that, which we will follow as a part of this course. So, to do that, because a major part of the course will deal with applications of numerical solutions or numerical simulations using the finite volume method, and one of the reasons is that this is a very common method which is well established. It follows from the conservation principles that we have discussed, and the exercise problems or illustrative problems that you will be doing as a part of this particular program, whatever you will be doing in Ansys platform, the corresponding fluid mechanics part is based on this algorithm or this method. So, as I always keep on saying that use of software, there is absolutely no problem, because it is a different era altogether. When we people were students, these kinds of software, not that they were not there, we are much older than most of you and all of you, but not from prehistoric era. So, we also had these software, and they were there in elementary form, and we were trained in all these, but in those days it was sort of what I would say suggested and very much emphasized that we will write the complete thing on our own by understanding the method, by understanding the algorithm, and coding it to the end whatever is our research or project is demanding. So, that was the sort of requirement in those days, but currently because of the availability of lot of open source and commercial either way software which you can tune for your own work, sometimes it is a wastage of time to reinvent a wheel. That means something is already there for your own project purpose, you may not always need to redo it. But what is the most important thing is that if you go through these at least for a few simple cases from start to the end, you will get the foundation of on which the software is there, and then the software will not remain as a black box. So, currently what happens is that I mean it is not desirable, but it happens that there are many people who work on CFD, but they do not have even a basic foundation on fluid mechanics, forget about CFD, and they are doing quite successfully, because at the end you need a software in which you give input and you get output, and output is typically very colored and nice pictures, and sometimes in our younger days very loosely we used to talk with our friends that CFD is more like colored fluid dynamics. So, that means you get nice colored plots, and they are typically to impress certain people, and sometimes people when they get into corporate they give it a more professional name, color for directors. That means that you may be having a lab director or project director who is interested to very quickly see what is the outcome. So, you can produce something and create a very good impression, but you do not know whether it is garbage in and garbage out. So, that responsibility is there with you, and believe me or not, if you do not have foundation on this subject, you will be lost somewhere in solving some problem, because you may be either using a inappropriate method, inappropriate choice of mesh, all these things can happen. So, it is very important to understand the physical thing, the method, and possibly a few simple cases where you can write the code on your own just to get a mastery on the topic. So, in this particular course we recognize that we are doing it in the modern era. So, I have kept it as a blended structure of traditional and modern. So, that means we will have all the essence of the good things from the traditional presented to you in the form of a capsule, and the modern thing you will do in parallel. So, that you become contemporary, but you do not lose the sort of the basic foundation, which is one of the challenges. And so, for that what you need to keep in mind, that so many codes, and many of you who may not have worked very significantly on CFD, but you have some familiarity with some of the codes, and some of you know that how to run such codes, I mean no matter for what problem that you have solved. So, we will try to see that what is the foundation, but before that what I will try to do is to give even a broader overview. So, whenever we are having a course on say simulations, we will advocate for simulations. This is what I would say is a biased view of presenting any topic. So, if someone is advocating experiments, that person will advocate experiments and then say that as if experiments are the first and last things in life. Someone who does simulations sometimes says that these are the first and last things in life, and this is good in a way that you are very passionate about what you are talking about and what you are presenting, but it becomes a bit of possessiveness, and when you have that possessiveness you lose that balance in from your purview. So, we have to keep in mind that at the end we are solving a physical problem. So, to solve the physical problem, be it applied to physiology or be it applied to any other application, you need to see that what is your purpose. So, experimental investigation is quite important and is quite good, and in fact if there is a reasonable way of doing experiments, that should be your first prerogative. Why? Because seeing is believing, and many things which you do with say theory, you are not able to reproduce what is exactly in the physical space. So, what you are doing is making an idealization of what is there in the physical space. Now, who will verify whether that idealization is right or wrong? So, it has to be either some observable data, may not be experiment, but something observed from a system, or maybe an experiment where the data is verified. So, in that extent, to that extent experiment you cannot really undermine, but there are challenges. So, why people look for alternatives is because there are challenges in something which would otherwise ideally be very good. Full scale experiments are very commonly expensive and often impossible. So, that impossibility, one example is this typical physiological scenario, like inside human body, let us say that you want to put a probe and find out velocity at every point, say where blood is flowing. This is impossible, no matter whatever investigation, whatever sophistication you have. So, that means it is impossible, not just physiology. Say let us say someone is working in a steel plant and doing a blast furnace modeling. So, maybe at very high temperature there is a melting of steel, and someone wants to see the flow of molten steel. So, at that high temperature, that and keeping in view that it is not a transparent system, you cannot do flow visualization. So, you have to maybe go for some scaled model which is simplified. So, in steel plant, for example, people use very commonly water models. So, that means you make a setup where you have water as a model fluid and you put a similar boundary condition and see what is happening in the water, because flow visualization there is more well established in the fluid mechanics. Now, people may argue that what is steel and what is water, like you are comparing apple with an orange, but fluid mechanics wise there is a lot of similarity. Heat transfer wise there is huge difference because their thermal conductivities, diffusivities are very different, but fluid mechanics wise the kinematic viscosity of water and steel are more or less the same, not exactly the same but of similar order. So in that way sometimes what we think as over idealized is not that bad. The another example is that organ on a chip or human body on a chip that we talked about. Definitely these are not human bodies, but something that we get out of this can be readily applied, but they will have simplification and it is often very difficult to extrapolate those results when you are talking about real life applications. And also measurement errors and other errors are there, experimental errors are inevitable and there are uncertainties, so many other factors which will mean that experiment is also not always seeing is believing, because the errors in the experiment can give you elusive output which is not the correct one, but because you have done the experiment without much control. So we keeping that in view, theoretical calculation is very good in a way that you work with numbers and there are sources of error just like experimental sources, but there are cases when there will be no sources of error. So what is that? When you have analytical solution, that means you have some equation, some boundary conditions which you can solve analytically. So if that exists and your equation is of course the physics which is correct, and if your boundary conditions and properties they are also quite correct, then analytical solution if it is there, nothing like it, because it will give you a closed form mathematical expression which is valid at each and every point in your space. But the challenge is that analytical solutions are usually not existing for most of the real life problems. They are existing only for some cases where you have lot of idealization, and usually mathematicians will tend to follow that idealization because their mind is occupied with the pleasure of getting an analytical solution. So the pleasure or success of getting an analytical solution will often compromise with the practical requirement, but analytical solutions are very important because even if it is not generalized, it will represent some limiting case of the general scenario. At least for the limiting case your other solutions can be tested, and in that way and it gives physical insight. So analytical solutions both intellectually as well as technically are very important, but you cannot get it for all cases. Numerical solutions you will get for almost all cases, because all you require is a geometry and a boundary condition and a set of properties and a code which will run to solve your equations. So if all these are on place, you can run no matter how complex the geometry is or the boundary conditions or properties, and you will get the solution. So now if you look into your problems for human health or physiology, you see that there is one very fundamental aspect which is biology, and there are new biological questions which are continuously being asked. Now if you have already a established model, the established model may not be in a position to answer new biological questions. So in that way you may require new technologies, but those new technologies also they have their limitations, but at least they can give data. For example, in an era when MRI, CT scan, all these things were not there, still patient data could have been obtained in other form of data which is not that high end data, maybe just blood pressure or maybe ECG like that. So with that data as an input, it could have been possible to solve some equations with that data as an input, at least through simulations. But now with more comprehensive medical investigation data, with the rapid advancement of these techniques like CT scan, MRI and all these, it is possible to get more detailed data which can be infused with the computation. Not only that, you can also do new style of experiments just like this lab on a chip based technologies, and that can also generate some data. So, with all these now you can have computation that can go very close to the physical reality. So, all I want to impress upon that let us be very positive and sort of in a way quite impressive about how numerical simulations can solve the physiological problems, but let us not be obsessive. So, we have to keep in mind that it is a holistic approach of solving a problem where many times the data available from either experiments or maybe medical tests for the health problem, they can enrich the simulations. So, we cannot just think simulation like you have an equation, you put some boundary condition and solve it. So, that may be very good for a first year maths course, but it is not good for solving a practical problem. So, I want this particular audience to be very sort of appreciative about it and not develop any bias, and because typically people have very extreme bias. The people I have been supervising students over the years, and my impression is that the students are usually very extreme. Some think that experiments are very important and they will like to do it, some think that experiments are useless and only they are very highly intellectual people, so they are very nice to do nice maths and computation. So, you have to see that that balance is developed in your mind. Whether you are able to do that or not is different, you may collaborate with others, but your open mindedness should be the key. So, with that we get into this modeling versus experimentation that I have talked about. So, modeling is cheaper in a sense that it is running in a computer, and computational facility with either your individual resource or shared resource is something which does not cost as much as a very high end sophisticated instrument and its running cost, and you get more complete information because you get point to point variation of all the variables which you want to solve. That kind of thing in any experiment it is very difficult to get, but some you can definitely get, but not so easy, and can handle any degree of complexity as long as there are so many ifs and buts, and that we will see, and that brings it to the limitation that it deals with a mathematical description and not with the reality, and the mathematical description can be inadequate. It may not be reflecting what is the thing, and consistency of the solution depends on different factors. So, we cannot really say that whether modeling is good or experimentation is good. What we can only say is that perhaps each of them requires the help of the other to get into the kind of solution that we are looking for. So, now when we look for the nature of solutions of what, so I will just start with the conservative form which we touched upon in the previous session. So, if you see the conservative form, so you have a variable dependent variable which is a function of position and time, no matter whether you use index notation for the coordinates or the standard xyz, whatever it is. So, you can have based on the number of coordinates required mathematically either a 1 dimensional, 2 dimensional or 3 dimensional problem. With respect to time as a variable, you can have steady or unsteady, and very interestingly the nature of the solution is something which would not just come from all these factors, but will come from certain physical aspect of the problem which can guide you to what numerical method you will be using. I am not getting into this topic, but I am sure all of you have done some course on partial differential equation at some point of time, if not a full course, at least some elementary part in your overall maths course. So, there is a classification of the partial differential equations, commonly we say parabolic, elliptic and hyperbolic equations, and it is very important to understand that the nature of the solution, nature of the equation, whether it is parabolic, elliptic or hyperbolic, will actually dictate what kind of numerical method we are going to use. So, let us take this example which is an one dimensional unsteady diffusion. So, if you put in place of phi temperature, it becomes the one dimensional unsteady heat conduction problem. So, you have some boundary condition, some initial condition that at time equal to 0 you have some value. Now, this is an equation where you have time as a coordinate and space as a coordinate, right. So, with respect to time, these are called as time marching problems. That means that you have something at time equal to 0, say you have a domain here at time equal to 0, every point temperature is something which is known. Now, suddenly you open the AC in the room. So, there will be a change in temperature over time, and say you are trying to make a simulation where you will put the input power of the AC and solve the temperature as a function of time. This is a very like a bread and butter problem in the room air conditioning, ventilation, etc. Now, to solve that problem, you have to keep in mind that now what is the temperature, and say we are going to work out the temperatures at subsequent times. We cannot influence what was the temperature 1 hour back, right. So, whatever was 1 hour back was 1 hour back. We can influence only what is going to happen from now till in the forward of time. So, this is called as a time marching problem. So, this time marching problem is technically a parabolic problem. So, that means you have a one way coordinate system. So, the one way typically time is a one way coordinate system, and there is a sort of a philosophical aspect to it. Sometimes we waste time in discussing what happened in the past, but what happened in the past is what happened in the past, we cannot change it. We can only take the lesson from that and move forward with that, and that is what even the mathematics is saying. This is where all subjects follow from, say, a broad philosophical perspective, that therefore, I mean the philosophy should be that better stop discussing about what happened in the past, just take the lesson from that and move forward. That is a time marching problem in life. So, you have a time marching, but space is not like that. Why? Because say at the center of the room somehow you have lit a candle and it has started heating. So, all parts of the room will get the effect of that. That means the effect is propagating in all possible directions, and that means that space wise you are having the propagation of this disturbance in all possible directions. Now, the disturbance can propagate in certain speed. So, if it is say just a simple heat conduction problem. So, if you create a disturbance like a change in temperature somewhere, so all other points will feel that disturbance by virtue of the fact that this disturbance will technically propagate at infinite speed in all directions. So, that makes it a problem which is an elliptic problem in terms of the differential equation terminology. But if the speed of propagation is finite of the disturbance, then it becomes a hyperbolic problem, just like a wave motion problem. So, if you go to a maths course, you will see that pages and pages of like derivations are given about parabolic, elliptic and hyperbolic equations, but people do not develop this physical feel of what are these about. So, when you are solving a physical problem, those pages of derivations are important, but to develop this physical feel about like how the nature of the influence of the coordinate is there, then that is very important. How? Let us say that you have a space coordinate and you want to solve the problem in the space coordinate. So, if it is elliptic in space, you have to be embedding that in your method, that the value of a variable at one point should be influenced by all the surrounding points, which are the typically grid points, nodes, etc. We will come to that. But if it is not like that, then it will be influenced by only grid points in a certain direction. And also we have to keep in mind that time is not the only one way coordinate system. You can also have space as a one way coordinate system. Let me give you an example, but if some of you have not done any advanced fluid mechanics course, you may not be able to relate that. We have something like boundary layer. That means you have say a solid boundary and over which you have a thin region in which the viscous effect is important, outside that it is almost like an ideal fluid flow. So, that thin region, how it is growing over the solid boundary is the growth of the boundary layer, and that growth of the boundary layer over that coordinate that is occurring, that is like a one way coordinate system. So, there although it is space, it is giving like a time like coordinate. So, one way is not always time, but it is a time like coordinate, and whenever you have a one way coordinate it is like time. So, you can give something like initial condition, although in a physical sense it is like a boundary condition, but in a mathematical sense it is like an initial condition. So, in that way, with this understanding, we now have to see that if we want to now solve this problem numerically, let us say, let us take one template which will be the agenda of this particular session, is one dimensional steady state. We will start with steady and then unsteady, but let us say a one dimensional problem of heat conduction. So, if you have an analytical solution, let us say yes, forget about heat conduction or whatever, say y is your dependent variable and x is your independent variable. So, if you have analytical solution, you will get a continuous function. So, you will get that, let us say this orange line. But if you do not have the analytical solution, what best you can do, so the analytical solution for a continuous variable is a continuous function. That means technically at all points you have your solution, although physically you may plot only in the graph a few selected points, but technically you have all points. Now, numerical solution is an abstraction of the original differential equation, where you are not attempting to solve the equation at all points, but some selected discrete points. So, breaking up your domain into a set of such discrete points is what is called as discretization. So, this is the first step to solve your problem, that you have a continuous domain and you are breaking that continuous domain into a collection of discrete points. One method of numerical simulation differs from the other in how to arrive at these discrete points, that method, but the goal is the same. And why you are doing that, there is a purpose. Computer cannot solve differential equations. Now, with AI it can do how, not actually it knows how to solve differential equations, but you can give some training so the computer can mechanically produce an output. But computer can actually take part in computing without training when you have algebraic equations. So, the whole ball game of numerical simulation is somehow recasting your differential equation to a set of algebraic equations. So, this is the central spirit. Sometimes the challenge is that when we are learning a subject, lot of I, J, K, big things, big lines, we forget about, or rather we do not know about what we are doing, and that is actually, according to me, is a defeat in learning a subject, because to write a thing with proper algebraic calculation, putting I, J, K meticulously, that someone trained can do, but that person cannot take further initiatives to take it forward, only can learn whatever is there in the book. So, with that objective, now you will not get an accurate solution. See this schematic which is shown in the graph. So, these circled points are your numerical solutions, somehow you have got it by running a code. So, they are not your exact solution. So, you have got some lost accuracy, and this is inevitable. Usually some accuracy will be lost, it may be minimal, but some accuracy will be lost. So, you rather would not like to have loss of accuracy. So, you want to have accuracy, but see everything in life it is a balance. So, you want to get a very high end thing, but you do not want to pay anything from your pocket, then you depend on lottery. So, similarly you want to get say high quality numerical solution, but you do not pay the cost of computation, that will not be possible in a real life problem. So, usually it is a trade off between what accuracy is acceptable to you and what is the computational cost that you need to pay for that. That is how real life what you are going to do with the computation in industrial problem or anywhere, this is how it is decided. So, in that way you will have loss of accuracy. So, you have to do an error analysis, that is numerical accuracy. Stability analysis, I will talk about that in brief. Numerical efficiency means how much computational cost that you have to pay, maybe CPU time or whatever. Validation, very very important, what you are getting is a result, and as I told you that with very outstanding development in the recent years on computer vision, computer graphics, etc., you can represent your result in a very nice way, sometimes with videos and all those things, and that then that can mask away the loss of accuracy. It is simply like if you have a smartwatch and you are so much fancied about it, you will never even argue that the blood pressure that the smartwatch is giving a reading, how close it is with respect to the classical sphygmomanometer reading. Nobody will ask this question because we are so much overawed by the smartwatch. So, similarly this is like a nice video going on with all the simulations, who will care what is the accuracy. So, again we were students of a certain generation where we were transiting from the old era to this new era, that was our student life. So, one of our professors at IISc made us very alert about this and said that we were talking about a homework problem of one of the courses where such graphs or plots were to be submitted. So, he gave a caution, he said that be careful, the amount of color in your CFD results is usually inversely proportional to the quality of your solution. So, in a way the reason is that it is a very loose statement, but he wanted to give the correct message that you have to be careful about all these things, like you have visualization, graphics and everything, but is it giving you the correct thing that you are looking for with a reasonable error. So, how we will know about that, and that is where we have to develop the correct foundation of we have to develop the correct foundation of solving the problem. So, if we develop a correct foundation for solving the problem, this is where we have to look into as a structure what we are going to do. So, we have a governing equation or a set of governing equations with initial and boundary conditions. So, that is like mathematical modeling. So, mathematical modeling is there for both analytical and numerical solution, because it is a mathematical description of the physical reality. Whatever assumptions you make, you list it down so that you know the limitations of your solution. Then for numerical solutions you need discretization, as I told you what is discretization. So, for that you have different methods, finite difference, finite volume, finite element, spectral, boundary element, immerse boundary, so many different methods are there. So, you can well imagine that in such a short course there is absolutely no way that we teach all these. In fact, each of these is a one full course. So, in that way our objective will be to give you a flavor of one of these, and that also overall flavor, not like the details of a full one semester course. If you want to see the details of a full one semester course, please look into my NPTEL lectures on CFD. You have nearly 50 plus lectures, and from that you will get the more comprehensive details. So, at the end of these you have a system of algebraic equations, and these are typically representing the values of the dependent variable at some discrete points, which in the language of different methods they may be grid, note points, etc. And then you use equation solver, typically if they are coupled, and if it is a linear system it will be a system of linear algebraic equations for which you need a what is a so called matrix solver, and this is something which from like a long time in the numerical analysis is so well established and so much classical that CFD can borrow that very easily. So, there are many established algorithms starting from the most what I should not call it primitive, but most commonly recognized and easily understood. I will go through that, the tri-diagonal matrix algorithm, TDMA or Thomas algorithm, in two names it is called, ADI alternate direction implicit, successive over relaxation, Gauss-Seidel method, Gaussian elimination, etc., etc. So, there are many such methods, and depending on the convenience LU decomposition, so many other methods are there, and if you have gone through any numerical analysis course, at least you have heard about this if you have not practiced all of them, and then you will get an approximate solution, and then you may plot it in the form of a graph or whatever, and that is your overall simulation workflow, and this does not change absolutely from the simplest problem in life in CFD to the most complex problem in life in the CFD. Now, but the detailing is there, and that is where we will get into the numerical issues. So, when we get into the numerical issues, we will come into one after the other, but very importantly what we are trying to do here is we are trying to make a check and balance that we have got some numerical solution, how reliable it is, how accurate it is. So, there are a few terminologies which are important checklists for the efficacy of your method. Number 1, consistency. So, consistency, what it means is that your original equation is a differential equation, and when you put it in a discrete form it becomes a difference equation, that means algebraic differences, some form of algebraic difference. Now, when you do that, how can you relate it with the original differential equation? What you can do is that you can have a solution of the original differential equation which you can always express in the form of a Taylor series. So, the Taylor series it is a functional form which will have infinite number of terms, that is what the Taylor series is. But because we cannot compute that all the infinite terms, had we been in a position to compute all the infinite terms it would be the correct solution, but we cannot do that. So, somewhere we have to cut it off, that is called as truncation. So, typically for many linear problems we trunk it off up to the linear term, first order term, and then neglect the terms which in maths books is written as neglecting higher order terms. So, you may have a question in mind that what is the basis on which you neglect the higher order terms. So, just recall that in a Taylor series expansion of fx plus h, you have fx plus h f dash x plus h square by factorial to f double dash x, and it goes on. So, your expectation is that you are working with small h, and because you are working with small h, h square is much smaller than h cube is even much smaller. So, if you keep up to h, all other terms are much smaller, that is your expectation, whether that is fulfilled or not is a different thing, and that is what is the meaning of truncating higher order terms or ignoring higher order terms, whatever you call. So, when you make that truncation, then with that truncated version of the function you are getting a solution. So, that what is the source of error? The source of error is truncating the Taylor series or equivalent, if you not call it a Taylor series, any other such series. So, in your numerical solution, let us say that you have one of the major parameters as the distance between the two discrete points. So, this overall can be thought of as a grid or a mesh, where you have two consecutive grid points and you have a distance between them. Let us say that distance is h in the Taylor series. So, if you consider the limit as h tends to 0, which you cannot do in computer, because computer will deal with maybe small numbers, but still finite small numbers. But conceptually, if you take the limit as h tends to 0 in your method, where you will have function of h, then your difference equation, which is the discrete equation, should in the limit represent the continuous differential equation. If that is there, then you can say it is a consistent discretization. So, consistency overall says that the truncation error in the limit as the grid spacing tends to 0 will be 0. Okay. So, this is conceptual, you can do it on pen and paper with the method. Stability is something that also you can do in pen and paper, but it deals with numbers. So, what do we mean by stability overall? So, in a physical system, stability means that if you perturb the system, disturb the system does not amplify that disturbance and get out of that initial stable configuration. So, that means that the disturbances are growing. So, in a physical system it can lead to a complete different solution or the physical configuration. In a mathematical system it can lead to a completely different unacceptable mathematical solution. So, where is the source of this? Every number which is calculated out of numerical computation has to be rounded off, right, and you may round it off to whatever decimals, maybe 48, 96, a large number of decimals, but that will not be the correct number, say 1 by 3. 1 by 3 no matter how where you truncate it is 0.3333, then it goes on. So, it is not exactly 1 by 3. So, there is an error because of the difference between 1 by 3 and that 0.333 etc. So, for one particular number that error is not important, all of us know, but when you are doing a numerical computation you are having a compounding of such calculations and that will make these errors compounded. Now, when these errors are compounded, it may so happen that let this error be compounded, but it will not blow up the solution in a different way or a different direction, then we say that it is a stable method. And if that blows up the solution to a completely undesirable direction, then it is an unstable method. So, to summarize, consistency talks about truncation error and stability talks about round off error. These two are two different errors in the analysis. Now, the main question comes. See, as an individual analysis we are not so much bothered about the theory of consistency and stability. What we want? We want that when we are solving the problem numerically it will converge to our solution that we want. So, that is convergence. So, our wish is the discrete solution tends to the exact one as the grid spacing tends to 0, with all round of error be there, truncation error be there, but this is the picture. So, even if it is consistent it will not happen like that if the round of error blows up. So, for certain types of problems consistency and stability together, in fact for all problems consistency plus stability together has to be looked into. So, for linear problems, that means the differential equations which are linear, consistency and stability together will ensure convergence. This is known as Lax equivalence theorem. So, if you have a linear problem, linear differential equation, be it ordinary be it partial, then if you have a consistent and a stable method you are sure it will converge. But if it is a nonlinear problem, and most of the fluid mechanics and other problems are nonlinear, so you cannot take this as a guarantee even though your method is consistent and stable. So, then only way to test the correct convergence of the problem is what we say as grid independence or mesh independent study. That means you have some grid spacing, then you refine it more and refine it more, and you see that as you are refining the solution is converging to some limit and it does not change as you refine it further. So, that has to be tested like a simulation experiment, but it cannot be theoretically talked about. So, now we come to discretization. So, if you have a time dependent problem and a position dependent problem, you have time derivatives and you have spatial derivatives. So, time derivatives no matter for whatever method we are using, we are almost exclusively using finite difference type of method. We do not call it finite difference because all methods have their own names, but the methods have their own names mostly because of the space discretization is different, but time discretization is more or less similar. space discretization wise you have finite difference, finite volume, finite element, etc., etc. So, here is a schematic view of what we mean by this. So, you have a continuous domain, you break the continuous domain into some subdomains with some geometric elements. So, the bottom picture is the continuous domain, it is you do not have any discretization. So, what you see at the top is you have discretized elements, or you may not have a discretized element, but you have some stencil of say horizontal and vertical lines, and wherever they intersect is the node point or a grid point. So, either of these two is possible. So, when you have that stencil without such element, that is finite difference, and when you have elements or control volumes, they become finite element and finite volume, but at the end they are represented by discrete points, be it an element or a control volume or intersection of stencil, it is represented by points. So, we will discuss about the finite volume, not just because your practical work in this course you will do using that, but also that it follows from the fundamental conservation principle. So, we talked about the fundamental conservation principle, that you have a control volume, something is entering and something is leaving, and you are writing a balance of that, that is in minus out plus generated equal to change. Yesterday in the previous session we talked about this. So, if you are now writing it in terms of the the mathematical functions, let us say J is the flux, so which is per unit area. So, you can write it in terms of the flux, flux in minus flux out, and you can see in the flux out it is something like the first order Taylor series that we have written, like Jx plus dx is Jx plus djx dx into dx, right. So, in that way we are representing the flux J, and because in the heat transfer problem J is minus k into dt dx, this is the Fourier's law of heat conduction, where k is the thermal conductivity. So, if you now substitute ddx of that Jx, where J is minus k dt dx and S is the source term. So, you have ddx of k dt dx plus S equal to 0. So, we will start with this simple thing, because it follows from the conservation principle, but always the simple situation will get you a complete feel and grasp of the method, where the complexity of a problem, if you start with that, you will get completely lost. So, in the finite volume method what we are doing, we are breaking the domain into a number of subdomains which we call as control volumes, and control volume you know very well, we have talked about that. These control volumes are like the dV, what we talked about in our this conservation principle discussion. But what is the difference between that dV and this we are discussing here? That dV was a differentially small volume, and this is a finite size control volume. Why finite size? Because your computer code cannot deal with differentially small numbers. So, it is a finite size control volume, but conceptually similar, and that is why the name finite volume, to make it distinguished from that differentially small volume. So, what we are doing is we are putting the differential equation and integrating it over the control volume. So, there is a nomenclature of the different aspects of the control volume. So, this is a rectangular control volume, there is no need for a rectangular control volume. When this subject was developed and advanced, in those days rectangular control volumes were most commonly used, because these different shapes of control volumes, their geometry, it was not adaptable to this type of method in those days. And this entire description of this subject, overall the finite volume method and its application to fluid flow problems, it was there for some time, but I would say that globally it has been made popularized to an extent that industry also accepts that as one of the major methods for all the CFD problems, is because of the what I would say as really pioneering contributions of one famous professor, Professor S. V. Patankar. So, Professor S.V. Patankar, Professor Suhash Patankar, he was of course he is still, I think he is quite aged, but perhaps linked with the same university, but he has been a professor of the University of Minnesota, and he had sort of mentored outstanding many outstanding students of him who have then became world famous, and they, so with their contribution primarily the Fluent software was originally developed. So, and his major contribution, and we will go through that, is advancing this method for solving the Navier-Stokes equation through two very important algorithms which are parts and parcels of every such software. One is simple algorithm and the other is the different variants of the simple, simpler, simplex, etc. So, all these have been due to him, and we have so many of the classical textbooks in this subject, but nothing has beaten that 1980 textbook, Numerical Heat Transfer and Fluid Flow, written by him, which is like this very thin, almost like class notes, but written in such a lucid language that you will completely understand it if you go through that. So, we have all learned the subject from the same gharana, like my supervisor from whom I learned, he learned from one of the students of Professor Patankar through classes. So, this is almost like a Gurukul that has been flowing from there to here. So, whatever I am showing is that has a very strong impression of what I have learned from those study materials and that book, which I believe may be out of print, but it is available from some source or the other, and I would consider that is the benchmark book, because everything else is based on some numerical advancement which is there many other forms of like research papers, etc., but these things are very fundamental. So, this nomenclature is also very fundamental. So, all papers will use this nomenclature. So, every control volume will be represented by a point which is the nodal point, that is P. Now, the control volume will have its faces. So, just to keep it physically meaningful, the left face is west. So, if you are going from left to right, as if we are going from west to east. So, the left face is west and the right face is east. So, W and E, but the name of the face is small letter, lower case. So, small w and small e, and the main nodal points or grid points by capital letter. So, whatever is the next nodal point, it is capital E in the east and capital W in the west, and this is the nomenclature. I mean, for all the books and all the study materials, when you code, you change them to I plus 1, I minus 1, etc. So, let us say delta x is the dimension of the control volume. So, what you do is you integrate it from small w to small e, that means over the control volume, it is a one dimensional problem. So, you have to keep in mind, okay, integration is a mathematical exercise. So, what you are achieving out of this? So, this is a principle of conservation of energy. So, by integrating it over this control volume, you are ensuring that this conservation law is fulfilled, and your domain is a collection of many such control volumes. So, if for one control volume it is fulfilled and you sort of sum it up for all control volumes, that means you have a mathematical foundation, in fact a discretization foundation, which is physically adhering to the principle of conservation, and that is why this method is so much physically appealing. So, now that you have the integration, how do you do the integration? So, if you look at the previous equation, it was the second derivative. So, the second derivative on integration will give the first derivative. So, first two terms are like that, and then you have the source term integrated, but your objective is what? Your objective is to convert this to some algebraic equation. So, that you can do only if you assume a t as a function of x. So, what will be your intuitive thing? That let us assume some polynomial t as a function of x, and you can easily differentiate that, and it will also be a polynomial function. But if you take any arbitrary polynomial and differentiate it, it will typically be a high order equation. So, let us say you take a polynomial like t is equal to a naught plus a1 x plus a2 x square plus a3 x cube, just I am giving an example. So, if you then calculate dt dx, so it will be up to x square. So, that means you will not get a linear equation. So, in that way, if you want to get at the end a system of linear equations, why your objective is linear equation? Because a system of linear algebraic equations has very robust method of numerical solution and you want to make use of it. Now, one may argue that no accuracy will be lost because say non-linear function if you approximate it by linear, but if your distance between the 2 points is very small, any non-linearity can be approximated by linearity. So, linearity is not bad provided you know how to linearize, and we will look into that. So, if you linearize, what we are doing here is we are approximating a piecewise linear temperature profile. This is called as a profile approximation. So, this is like you are taking an approximate function of the dependent variable, say temperature, as a function of x. So, if you make that linear, then dt dx is constant if t versus x is linear. So, you cannot take the full domain linear because then it will be lot of error. Only between two grid points you take linear, and if the grid points are close, that error does not matter, that is your intuitive expectation. So, dt dx will be simply the difference divided by delta x. So, that is what is written here. So, now if you substitute that, then you will get a very simple linear algebraic equation, which is AP is a coefficient, AP into TP is equal to AE into TE plus AW TW plus B, where AP, AE and AW are some coefficients which are these, and physically like AE and AW are like conductance. That is the physical meaning. If you do not know the physical meaning also okay, because it is just coming out of your calculation. So, what you see here, the most important observation, that temperature at the point P is influenced by temperature at E and W. So, this is a true representation of an elliptic problem. That means at a point it is influenced by neighbors in all sides. Okay. So, in that way for every point P you will have this equation. Now, we had the source term S, but we do not yet have a standard way of integration of integral S dx. Why that is important? Because source term can also be a function of temperature. So, let us say that the source term is a function of temperature. So, you can take the source term as any arbitrary function of temperature again as what the profile assumption, but the finite volume method gives a flexibility of taking the source term, its dependence on temperature, in a manner which is different from any other temperature variation that you have taken for other terms. So, you do not have to take the approximating function same for all the terms, that flexibility you have. The reason is that this is only for the integration, and once that integration is done, its history of how the integration is done may be lost, that is not important. So, when you do that, what is done here is that simply it is considered that over this entire control volume. So, let me go back to the previous slide. So, maybe one slide back. So, you have the control volume and P is its representative node point. So, the source term formulation is taking that the temperature at P, whatever it is, the same is throughout the control volume. That means a piecewise constant temperature. So, piecewise constant temperature is even a further simplification of a general linear variation. So, we will see that whether that sort of creates any problem or not, because otherwise it is quite simple to do in terms of the analysis. So, then if your source term is a function of temperature and temperature is constant, you can take it out of the integration and integrate the dx. So, if you do that, we will get back to that slide. So, if you take that source term as a constant with Sc plus Sp into Tp, and Tp is a constant, So then your integral of dx will be that delta x, and if you then put it in the equation you will get this overall form where you also have integrated the source term. So now so this is what is your discretization, and you usually do it on pen and paper. This is not you do in a computer. So the question comes that before trying it out in the computer you should make an initial assessment whether it is likely to be physically realistic or not, and that for that there are certain guiding principles, and the overall guiding principle is the solution should always be physically realistic. This is very important, and this even without anything from common sense we have to understand that whatever by maths we are doing it should be physically realistic, and from physical consideration as well as mathematical consideration the balance of flux should be maintained. That means what? So let us say you have a slab and you have a heat conduction from one end of the slab to the other. So if you take every section and it is steady state, the same heat flux is flowing. So that flux consistency also has to be maintained. So if the flux consistency is maintained and solution is physically realistic, even if your exact solution and approximate solution somehow because the graph is in a very light color you are not able to see it, the exact solution you can see approximate is some approximate variant of this, there is inaccuracy but acceptable because at least it is satisfying this. So you can see that the exact is this that light colored thing and approximate is this deep colored thing. So the light colored thing which you cannot see really very well is almost the the approximate one, and this is where you have error but accepted. But if you have this one as a continuous function with no maxima minima, monotonic function, and you have an approximate solution with some maxima minima, then that is physically wrong. So that you have to see that that is not happening. So how will you test that? So Professor Patankar then put forward these 4 rules which are called as 4 basic rules. So what are these? Rule 1, flux consistency at control volume phases. So when you have a phase which is common to 2 adjacent control volumes. So let us say you have one control volume and another control volume, and you have a phase common to that, the flux across it must be represented by the same expression. That means it is a continuous flux, so to say. So this is quite understandable, but we have to see that it is really happening. Rule 2, all coefficients of the discretization equation must be positive. So the more fundamental way of telling is that all the coefficients should be of the same sign, be positive or negative. And if you now look into that, I will go back and forth. So see the coefficients AP, AE, AW. So you have AE is positive because it is thermal conductivity by some physical length, AW positive. So you will want that AP is also positive. So what can make AP negative potentially if SP is positive, right? So if SP is positive, overall AP may be positive or may be negative depending on SP, but you should not keep it a chance because every different simulation may have different SP values on which you have no control. So to make it airtight, your formulation should make SP itself negative so that you always have AP positive. So that is what is formalized through this, which is that negative slope of the this linearization of the source term. That means if S is this one, that SP must always be negative, or I don't know, it may be 0 also. And another rule 4, that AP is the sum of the neighboring coefficients if there is no source or sink. That means what? Let me come back and see how this follows from the maths, the basic mathematical thing. So if your SP is 0, that means there is no heat source, then you have AP is equal to AE plus AW. Now this has to be satisfied. Why? See, if that is not satisfied, then if you look into the differential equation, let us get back to the differential equation, sorry, original the differential equation from which we started. Yes. So, see the d dx of k dt dx plus s equal to 0, let us say k equal to constant and s equal to 0. So, you have d2t dx2 equal to 0, which is the simplest equation that you could imagine, second order. So, for that equation, if t is equal to t1 is a solution and t equal to t2 is a solution, then t equal to a linear combination of t1 and t2 is also a solution. So, that is a hallmark of a linear equation. So, when you get a solution, your solution will also represent that hallmark, and that is possible only when you have AP is equal to AE plus AW, otherwise that linearity is not possible, you can verify it very easily. So, the whole idea is that whatever is the physics and the maths that your original differential equation is carrying, your discretized equation should also carry more or less the same thing conceptually. So, that brings these 4 basic rules, and it is very important because even if the problem is very conceptually demanding, still you can do that. Now, we focus more on properties. So, in the discretization equation you have seen that we require the thermal conductivity at small e and small w, but usually for a problem when you describe, the properties or any input they are given at the main node points capital P, capital E, etc., not those small e and small w. So, you have to interpolate. So, before interpolation, let us look into the physics. Let us say we have a heat transfer problem where this problem is divided into 2 slabs. It is like one of the first courses of heat conduction problem. So, heat is transferred from the left to the right and this control volume is divided into 2 slabs. So, you have the heat flux at small e, which is k into the temperature difference by the delta x. This is a Fourier's law in a linear form, and you can now, so if we break it into 2 slabs, one slab is having the length delta x E minus, another delta x E plus. If just look into the figure and you will know what they are. So, you can write the flux at small e by considering the left slab and the right slab separately, but they should be the same because of the continuity of flux. So, if you now equate all these, you will, what you do simply is like add the 2 together. So, QE, if you add both the numerator and the denominator, you will get the last equation that you get at the bottom. So, whatever QE is the expression at the top should be same as QE what is written at the bottom. Okay. So, you have to see that your discretization and your interpolation of property should be satisfying this. So, now for any interpolation, so this is always our challenge. We have a mathematical fixed mindset and we have a physical mindset, and usually we never consult these two. So, when we do maths, we forget about the physical world, and when we do physics, we do not care about the mathematical world. So, because we normally do not talk with that physical world, for any property at the interface, what we will do? We will do a linear interpolation. That means we will say k small e should be some linear interpolation of k at capital P and capital E which are known. So, that is what a formula that we have written. And what is this f small e? It is the proportion of the 2 lengths delta x E minus and delta x E plus. So, if they are equal, then this is half, right. Many times you can take equally spaced grids, so that is half, but if you do not take it, it will be some number between 0 and 1. So, now if you take that example when they are equal, then Fe is equal to half. So, this is what you will get the value of k small e from your consistency of flux, what is written at the top, whereas the linear interpolation gives what is there at the bottom. you take f equal to half, then k small e is just the arithmetic mean of this, and in fact the physical thing is giving the harmonic mean. So, see where mathematical intuition fails. Interpolation we always try to do linear, which for equal space becomes arithmetic mean, but the physics says that it has to be harmonic mean. So, whatever we do, any formulation, what is emphasized here is that we should not lose this physics and just take a blind interpolation and put it there. Okay. So, if we put that thing, then the next okay. So, just for a change, okay, let me do this. I have put a sample problem like example problem. So, you have a source term. So, I talked about putting a source term as a linear function, but sometimes the source term is non-linear. So, how do you linearize it? So, this is one such example. So, there is a flow through a porous medium where the in the x direction momentum equation or flow there is a resistance against flow, that is why minus. So, S equal to minus C mod of u into u. Mod of u is always positive and u depending on the direction. So, if it is u in positive x, the source is in the negative x. So, it is like a friction drag. So, physically it is like friction in a porous medium. So, if you want to now model this source term, how do you linearize it? So, this is the solution I have outlined here, very simple. So, what you have to do, you have to keep in mind, and this I am just telling you maybe the principle behind this. So, you have a graph, you want to linearize this at a point, let us say this is the point, this represents the point P. Okay. So, you want to linearize it. What is the best linear representation of any non-linear graph? The tangent, because that represents the first order derivative correctly, and the derivative up to which it can be represented correctly for a linear representation is only the first order derivative, other derivatives cannot be represented. So, what you do, say let us say this is say S versus x. So, you take this one which is approximating this, maybe overall globally it is incorrect, but locally it may be alright, or instead of x s I write y, because you can relate it with your coordinate geometry, what you have learnt in school. So, let us say that this point is x naught comma y naught. So, what is the equation of this straight line? So, y minus y naught is equal to m into x minus x naught, right. So, this m is the slope of this, what is this? This is dy dx at x naught comma y naught, right. So, you can write y equal to y naught plus dy dx at x naught comma y naught into x minus x naught. So, this is a linearized version of this, whether it is correct or wrong in the physical sense is something else, but maths wise this is the best that we can do, right. So, that is what I have written. So, at a point star s minus s star is ds du at that star into u minus u star. So, instead of y versus x, it is now s versus u, and your given point is the star at which you are calculating it. Okay. So, now if you do that, and so because it is mod, for any problem where you are working with mod, it is better to take two cases, one is greater than 0 and one is less than 0, because we all know that mod x equal to x if x greater than 0 and mod x equal to minus x if x is less than 0. So, that is what we have taken, and in the first case where u is greater than 0, we see that Sp is negative, because u star is greater than 0, C is positive and you have minus. So, it makes Sp negative. So, that follows that rule, but if u is less than 0, then this source term linearization, you will see that because u star is negative, So, you will have this one. So, Sp, if you take this 2C U star, so if your U star is negative, you will have Sp also negative, right. So, in a way you have checked that both are negative. So, in this case it is alright, but if that is not what you will do, let us say it does not come because you are given some function and it has somehow given it has positive. So, then what you can do, see you have S equal to Sc, which is a constant term and a linear variation term. So, then you can put that linear variation as 0 if it is giving Sp as positive and dump the everything on the constant. You may argue that you have a variable, how can you dump it as a constant? In an iterative method, at every iteration when you put that value, a variable becomes a constant. So, you can use an iterative method and put that value at that particular iteration, whatever it is, everything dumped onto Sc and not on Sp. So, now the boundary conditions, I will talk about the mathematical language of the boundary conditions. So, you have a given boundary temperature which is possible, you have a given boundary heat flux. See, I am trying to develop a mathematical foundation on the basis of a simple physical foundation which may be easy for you to grasp. So, the heat flux, we all know that Fourier's law of heat conduction means that your heat flux is related to the temperature gradient. So, that means that you have either the temperature given or the temperature gradient given, but there can also be a possibility that temperature gradient itself is a function of temperature. So, you have three possibilities, one is temperature given, another is temperature gradient given, third is temperature as a function of temperature gradient. So, to generalize, the value of the dependent variable given or the gradient of the dependent variable given or the gradient given as a function of the variable. So, if the value of the variable is given, it is called as a Dirichlet boundary condition in mathematics. If the gradient is given, it is called as a Neumann boundary condition, and if the gradient is given as a function of the value, it is called as a mixed boundary condition. So, it is either of these, but the physical situation also is like that. So, this is the way by which how do you give boundary conditions. So, if temperature is known, then okay, for that boundary you do not have to solve. So, that is there, but if heat flux is given, then what you can do is you can take half control volume which is given by the blue color and you integrate your governing equation and apply that heat flux there to get another discrete equation. So, that example is given here, that you take that control volume and if you integrate that that k dt dx, it becomes heat flux. So, one of the boundaries heat flux is given, so that is a given number qb, and others you can write, so that now you see an interesting thing, that temperature at the boundary is given in terms of the next point I, but there is nothing in the left of the boundary. So, this is a very interesting thing, that although it is a two-way coordinate with the elliptic problem, but at the boundary it becomes one way, that there is nothing in the left of the boundary, and that is how you can start propagating the solution from the boundary, and that is physically implementing the boundary condition. So, now what you have a system of algebraic equations, right. So, just a minute. So, you have at every point P this equation form where APTP is equal to AETE plus AWTW plus a constant B. So, now if you code it, it is like AITI equal to BITI plus 1 plus CITI minus 1 plus DI, right, where for I equal to 1 and I equal to n, which are the boundary points, you if temperature is given, then like for example if you have this 1, so then you have, if temperature is given, then you do not have to solve it. If temperature is not given but flux is given, you still have A1 T1 equal to B1 T2 plus D1, but there is no T minus 1 or T0, right. So at the boundary it is only one neighbor, other points 2 neighbors. So we have this system of equations. So if you have this system of equations, then how do you solve it? So this is that tri-diagonal matrix algorithm, and this is so famous that there is a company, Tri-Diagonal Solutions, in Pune, one startup which is doing very well. So this is like a symbol of whoever has learned this course, it is a CFD company. So what you do is you write this very simple algorithm, but I am trying to explain it a bit more. So at the boundary what you have is Ti equal Ti minus 1, for example, say if W was there at the boundary. So Ti minus 1 is equal to Pi minus 1 Ti plus Qi minus 1. So how it comes, let me give you a specific example. So let us consider one particular case. Let us say that you have, I am just putting a point 1, 2, 3. So you have say maybe 4. So for the point 2 on the point 1 I am writing the equation. So you have A1 T1 is equal to B1 T2 plus say D1, right. So this is now your point P, this is the right, left there is nothing. So this is for the point 1. For the point 2 you have A2 T2 is equal to B2 T1 plus Bi Ti plus 1 B2 T3 plus C1 into T1 plus you have this one C2 into T1 plus D2, right. So now so you know from here that you can just simply write it T1 is equal to B1 by A1 into T2 plus D1 by A1, right. So now if you substitute that here, so it will be something, let us say we write it B1 by A1 into T2 plus D1 by A1, right. So now you have a term with T2, this one, which you can club up with the another coefficient which is there as T2. So you can write it now T2, and if you clean it up, that T2 will be a function of some constant will come into T3 plus another constant. So the boundary is helping to write in this form that T at one point is a coefficient into T at the next point plus a constant. So that is why we can write that in the form Ti minus 1 is equal to Pi minus 1 Ti plus Qi minus 1, okay. So the question is that now that we have this, we do not know what is Pi minus 1, Q minus 1, I minus 1, because our original discretization gives Ai, Bi, Ci, etc. So how do you get this? So what we do is that, assuming that to be of that form, in the first equation in place of this Ti minus 1 we are substituting Pi minus 1 Ti plus Qi minus 1, okay. And then if you simplify you will get this, the Ti into something into Ti plus 1 plus something, and if you compare that with the Ti equal to Pi into Ti plus 1 plus Qi, then you will get Pi and Qi in terms of Ai, Bi, Ci, Di, just comparing, right. So that means you now already have a formula where if you have Ai, Bi, Ci, Di, you can calculate Pi and Qi. For I equal to 1 you already know from the boundary condition, So, for I equal to 1 you have A1 T1 is equal to B1 T2, so C1 equal to 0, right, and for I equal to n you have Bn equal to 0, because there is nothing called as Tn plus 1, okay, and then you have P1. So, if you see P1, if you have C1 equal to 0, that means P1 is B1 by A1 and Q1 is similarly D1 by A1. So, you can start with, you know, P1 and Q1, and then you use this recursive formula to calculate Pi and Qi for the rest of the I by running a for loop, okay. So, this is the algorithm, calculate P1 equal to B1 by A1 and Q1 equal to D1 by A1, use that recursive relation, the formula that we showed in previously, to get Pi and Qi and set Tn equal to Qn, and then you can use the recurrence relation to get the other points. So, the first set, so if you see that you get Tn equal to Qn in a formal Gaussian elimination, this is forward elimination, and the last one is Ti equal to Pi Ti plus 1. What you are doing? You are getting the previous point's value from the next point's value. So, this is the back substitution in the Gaussian elimination. So, whatever is the forward elimination and backward substitution in Gaussian elimination, you are able to do that in a much simple way, because in a Gaussian elimination you are generally talking about a matrix which is flooded with values, but here you have only 3 diagonals. The main diagonal for the main grid point P, the upper diagonal for the grid point capital E, and lower diagonal for the grid point capital W for each of the points. So, because your coefficient matrix has many zeros with only these 3 diagonals present, this is called as a tri-diagonal matrix, and a matrix requires a 2-dimensional space for its in the memory I comma j, but because you have these 3 diagonals, the algorithm is like creating a pseudo 1-dimensional way, so that with one index I you are able to store and compute with this. That is what the computation is doing. So, in that way, so now I will go through the unsteady heat conduction. So, for the unsteady heat conduction, we have this equation. So, in the unsteady heat conduction, what we are doing, we are now having an unsteady term. So, for the steady term we have seen how to integrate it, okay, but now we have added a dimension. It is not the space dimension, but the time dimension, okay. So, when you have that dimension added, so what happens here? So, you have your time from t to t plus delta t and space from small w to small e, okay. So, in that way you are integrating with respect to time some functions. So, what you are integrating with respect to time? Number one, the space terms which you have discretized, those also have to be integrated over time, and the time dependent term also has to be integrated over time. Because it is a continuous function, it does not matter whether you do the time integration earlier or the space integration earlier. So, for the time derivative we will do the time integration earlier, for space derivative we will do the space integration earlier. So, now when you integrate with respect to time, the time dependent term is very easy. So, what you do, so let us say rho into C, that is density and specific heat, they are constant. So, if you now integrate it, it is just the value of the temperature at the new time, which is T plus delta T minus the old time, okay. So, then that is quite clear. In the right hand side, what you are doing? Now, space integration we have done first, and this is same as that what we did for the steady state problem. So, we have to integrate something of the form temperature into dt, where t is time, from small t to t plus delta t, where the temperature can be at E, P, W, etc. So, our entire new learning from this is how to do that integration in a discrete form for integral of temperature into d of time. Okay. So, let us try to look into that. So, this is what we call as time integration. So, when you have a time integration, so we can, whatever is the time integration, the outcome is that the temperature at that point will be dependent on the temperature at the beginning of the time step and temperature at the end of the time step. These are the two discrete values. So, we can write it as a weighted average. So, in that way we can use that value of interpolation function f, where f will tell how much weight will be there for the beginning of the time step value and how much weight will be there for the end of the time step value. So, if f equal to 0, you can see that the entire effect is on the end of the time step. Okay. So, there may be a plus minus sign there, typo, that just you can fix it very easily. So, if f is 0, you are getting that integral should be just Tp old into delta t, right. If f is 1, then it would be Tp new into delta t. So, f equal to 0 means the result of the time integration depends on the value only at the beginning, and f equal to 1 means the result of the time integration depends on the value only at the end of the time step. So, conceptually it means what? That over the entire time step the temperature is primarily decided by the value either at the beginning of the time step or end of the time step. So, if it is at the beginning of the time step, you can see the graph for f equal to 0. So, overall for this entire delta t, it is this old means the beginning of the time step, and suddenly it jumps to the new value. So, overall the entire time it is almost the old value. So, this is called as explicit. Why it is explicit? Because you are able to write what is now as an explicit function of what was there delta t time back. If it is the other way, that is temperature at now is more or less related to what is temperature at now, but we do not know what it is, that means it is implicit, that had we known what is the temperature at now, we would know what is it based on this functional dependence. So, if you see the lower graph, so that is the explicit implicit, that is f equal to 1, that means almost over the time step you have this temperature equal to the new. In between, if you take for example f equal to half, you can say that I will play my safe card, I will not take either of these, but maybe half of this and half of that and take a linear variation. This is called as Crank-Nicolson scheme. So, depending on the value of f, you can switch this algebraic expression to explicit, implicit and Crank-Nicolson. So, now we will discuss about the two extreme, explicit and implicit, and I would usually prefer either to use this but never Crank-Nicolson. The reason is that these are extremes and their advantages are well known, limitations are well known. If you are taking something in between, you are carrying the limitations of both. So, that either way you take at least advantage of one instead of taking the limitations of both. So, explicit method, if you write it, you will get this your expression. So, you have APTP is equal to AE TE old plus AW TW old plus something into TP old. Okay. So, you have to keep in mind that now not just there is a physical neighbor, there is also time neighbor. So, physical neighbor is for P is E and W, for time neighbor the P now its time neighbor is P old. So, you have a time neighbor and you have a space neighbor. So, in that way it is written the left hand side in terms of the right hand side, the first two will talk about the time neighbor, space neighbor, and the last one the time neighbor, but the space neighbor also is described on the basis of the old temperature value, because the explicit scheme says that everything is the temperature at the beginning of the time step. So, if you do that, now recall the 4 golden rules, all coefficients have to be positive. So, I know here same sign, but here AE and AW are positive, so the last one also has to be positive. So, the last one, if it has to be positive, you must have AP old greater than AE plus AW, and that brings to the last equation. If you take all the grid lengths just the same, just for simple algebraic calculation, so your delta T becomes less than this one. So, this means that to solve this problem without having negative, so what will happen if a coefficient is negative? So, what you expect is that if you increase the boundary temperatures, the temperature at that point will also increase. So, that means you have a point P, W and E, if you increase the temperature, P temperature should also increase. But if one of the coefficients is negative, other is positive, we will see increase will create a decrease effect, which is physically unrealistic. So, to avoid that physical unrealistic nature, you have to make that bracketed term positive, and that will give this delta T less than this. So, you have a time step constraint based on your delta x. So, that means you cannot choose any arbitrary time step, you lose the choice of freedom of your time step completely, and it will be guided by the choice of your space step delta x. Now, this is a constraint, but what advantage you get? See, when you are solving this, entire right hand side is known because old is known. So, you are able to solve this without coupling with any other equation. So, your entire matrix solver is not required. So, whatever may be the TDMA, Gauss-Seidel, Gaussian, nothing is required. You have left hand side, right hand side is completely known, in that way you keep on marching with time. Okay. So, you are gaining a lot in the simplicity of your solution of equations, but the delta T is a big constraint. The implicit scheme, if you see, now I have got rid of that superscript, the new I have not written. So, everything has a superscript new. So, now in this you do not have any of the coefficients which can become negative. If you take SP as negative, then all become positive. So, the implicit scheme will not have any constraint of the time step. So, you can choose any time step, it may not be accurate, but it will give you physically realistic, but the cost that you have to pay is that now you have to solve a system of coupled algebraic equations, which is the matrix solver. So, again this is the lesson of life, you gain something and you lose something. So, you have to decide. Sometimes what people do is prefer an implicit scheme. Why? Because before standardizing a CFD problem you have to make a lot of trials. So, to make the trial you can keep a coarse time step and see at least it is giving physically the correct thing, but the explicit scheme coarse time step you cannot keep, because that can give you wrong results. Now, just to upgrade it to 2-dimensional problem, you see that there is just a simple change, that your integration from 1-dimensional will become 2-dimensional. So, you had the points W and E, and now you have the points N and S, north and south. So, conceptually the same, just a double integration. So, you will get the same form, but you have more neighbors now. So, clearly now you do not have a tridiagonal system. So, and then but still it is a sparse matrix, that you have only a few neighbors and others are 0. So, there are ways of handling this, but you can convert it to a tridiagonal problem by assuming some iterative scheme, but not directly. And for 3D again the same. So, for 3D you have the top and the bottom. So, for 1D east and west, 2D you have north and south added, for 3D top and bottom. So, that makes your 3 dimensional structure, but again the equation looks all the same. So, if you know how to solve the 1D problem, you also know conceptually how to solve the 2D and 3D problem, and that is why solving the 1D problem is of great value. Now, it is quite clear that if you want to cast the 2D and 3D problem to a 1D problem, that then you have to assume some values in the other dimensions, and that means you have to go for an iterative scheme with some assumption, maybe an initial guess. So, when you make an initial guess and you start with an iterative method, your guess may be so bad that your method is going to deviate you away from the actual solution. So, how to put a control on that, and that is what is known as the relaxation. So, this is a trick that all the numerical CFD people will play. See, every field has a trick. So, this kind of trick, how to handle this, the kind of trick is a matter of mastery and experience. More you work with it, more you will know, but I will give you a broad idea of what is this trick. So, let us say that you have your solution as, say you are having your solution as t, and you are having your iterative solution, the previous iteration as t previous. Okay. So, if your t is equal to t previous quite close, that means you are going to convergence, but in general they are not the same. So, what it will be? It will be t equal to say t previous plus t minus t previous, right. This is something which is so obvious that it is like x equal to x, but I have written it with a purpose, right. So, this is always true, but now what I do is I multiply this with a factor alpha, then this is not true. When this is true, it is true only when this is 0 or very close to 0, okay. But this is now my handle. So, what I will do is, see, you are starting with a guess and iteration is moving. Sometimes iteration is out of your control, it is taking the solution, diverging, that many times students say that, sir, we are running it but it is diverging. So, my only recommendation, if everything else goes fine, you control the change, perhaps with every iteration it is changing too fast. So, what you do? So, this is your change. So, to control this change you use something which is between 0 to 1, but typically less than 1. So, less than 1, if it is going much out of control, you use a small number, not too small, because then you will never be able to traverse to the convergence, but something reasonable, say maybe it is not that bad, but you want to control it, maybe 0.5 like that, just I am giving an example. But there is no such rule, you have to problem to problem you have to adjust it. So, this is called as a relaxation factor. Sometimes you can also use it greater than 1, when it is slow you want to accelerate it. So, depending on that you call it under relaxation or over relaxation. So, then what you can write is t, so 1 minus alpha into t is equal to that so 1 minus alpha into t is equal to t previous into 1 minus alpha, right. So, in that way, so sorry, yes. So, now what you see, sorry, so t equal to t previous plus, yes. So, now if you multiply it with alpha, so let us see t, then 1 minus alpha and then t previous into 1 minus alpha, right. So, now see, technically it should not depend on what is alpha, right. It will depend only if t is not equal to t previous, then left hand side and right hand side is not the same. But when t equal to t previous and that is your objective, say your objective is to climb the Mount Everest, whether someone drops you from helicopter or you take a donkey or somehow you manage it, or you give someone a bribe so that you sit at your home and he declares that you have gone to the Mount Everest, all the same for you, you want a social media hit. So, that is it. So, the whole idea is that you want to get a converged solution, Now whether you go whatever alpha you use does not matter so long as you convert. So this alpha is a handle which is available to you so long as you come to finally the state when t is approximately equal to t previous, and that is what is your convergence anyway in an iterative method that you have to achieve. So that alpha is called as the relaxation factor. So that is using that alpha how your method can be applied with an iterative scheme, that is what is given here. So this is the of course the discretized equation, but the concept I have given through a simple equation. So I have given two homeworks. So I have made some effort from myself, so you should also make some effort from yourself, right. So two homework problems, and they are like, so you have a one dimensional steady state problem. I mean you may take a photo in your phone, but I am just telling what it is. So you have this one dimensional steady state heat conduction problem, but source term is A minus Bt square, it is given to you. So you derive the finite volume discretization by assuming a piecewise linear profile in the temperature in both the diffusion means the conduction term, which we have done exactly the same, and also in the source term that we have not done, and write the final discrete equations and examine whether your discretization violates one of those 4 basic rules or it satisfies. So this is number 1, and number 2, the second problem is the same unsteady problem but in cylindrical coordinate system. So you discretize and develop the finite volume method. So now the only thing that you have to do is that in a 2 dimensional space your elemental volume is what, say dx into dy, and in a r theta space it is r d theta dr, right. So whatever you integrated with respect to dx dy, here the right hand side you have to integrate with respect to r d theta dr, that is it. So if you have understood that how to do that integration, you will be able to do this. So these two will be your assignment homeworks. How we will move in this course is that we will have such assignments homeworks. So this is like pen and paper assignment homework to make you familiar. We will have computer assignments and homeworks. Some will be simple coding from the scratch, some will be use of software, and all the combination of these will be looked into for your final assessment. We will not have any such pen and paper exam. For such a course it is not going to work. So it is more like practice and this kind of assignment based.